Well, hello, boys and girls. It's nice to have a chance to see you all. If I could see you all, that would be. I hope you're all well. Um, Sadly, I'm not teaching on campus as I said I would. I'm at home, and I'll do my best to try to help you complete the course. If you have any questions about anything, any comments, just let me know, and I'll do my best to address whatever it is. For the moment, what I want to do is to start in on the next part of the course. I'm assuming here that everyone uh, has made sufficient progress on the lab that you can turn that in by Friday. In the meantime, I'm going to start talking about maximum likelihood estimation, which is the next part of the course. And so what I want to do today is just to talk about maximum likelihood sort of in principle, how it works, and give you a couple of examples. And once we have done that, we'll talk about some specific maximum likelihood estimators, Logit, Probit, Tobit, and a couple of others, I think. And we'll see how that goes. At this point, I'm assuming that I'm probably going to do this lecture in a couple of different pieces. I've been doing lectures for Econ 301, and it seems like several shorter segments is better than one long segment. And so that's probably what I'll do. I'll probably break this into a couple of segments. I'll let you know as we go. So what is maximum likelihood estimation? With maximum likelihood estimation, it's a different approach to estimation than what we've seen before. It's not least squares. What we do is we have some outcome of interest, and we need to have some idea of how that outcome is distributed. Is it normal? Does it have some other sort of distribution? And once we know that, what we do is we look at the observations that we have from our sample and ask the question, what values of the parameters for the distribution are most likely to have led to this sample? Okay, so I know that maximum likelihood, sort of describing it, sounds circular the first couple of times you hear it. Once you see it used, you start to get a feel for it. So what I want to do is to go through a few different examples today to try to give you a feel for how maximum likelihood estimation works. And you're probably going to have to think your way through this a couple of times to really understand it. So what I'm going to do is I'm going to switch cameras and make you keep you from having to keep looking at my face, which is, I know, a hardship. And I'm going to allow you to see a piece of paper that I'm going to write on, and hopefully I'll talk and we'll be able to make some progress here. So there it is, paper. So let's just start with the simplest example possible. Imagine we have samples from a population, and the sample size for each of those samples is, let's call it 1,000. Okay, so we've got a bunch of samples, and for each sample, we can compute X bar, the mean. Okay. If we think about all those X bars, if we have a whole bunch of samples, we're going to have what we call the sampling distribution of X bar. And what we know about it is that because of the central limit theorem, we can say that this sampling distribution is distributed normally with mean mu, standard deviation sigma, or variance sigma squared. Okay. Get you a little bit closer here. There we go. So you got a bunch of X bars. And what we want to do is to try to figure out what mu and sigma are. So let's draw a picture of the situation. We have an axis. This is the axis for our sampling distribution of X bar. And what do we actually observe? Well, we have X bars distributed along this axis. We've gone out and we've computed some X bars. And we can distribute those along the axis. And what you can see from the way I've done this is that the X bars tend to be sort of clustered in here and a little bit more sparse as we move away from, from the center of that axis. And the question we want to ask is, given the X bars we observe, what values of mu and sigma are most likely to have generated this sample? And so just thinking about it graphically, we might say, well, there's a normal distribution, okay? But it seems like if we were to move the distribution in that direction, that would improve the fit between the data and the distribution. And so maybe what we want to do is to move the distribution over here. And maybe what we want to do then is to change the variance to bring the to make the distribution more tightly clustered. Maybe it would make sense to think about the distribution more that way. So we can adjust mu by moving the distribution left to right. We can adjust sigma by making the distribution more concentrated around its mean or less concentrated. And we need to have some criterion then for deciding exactly when we've achieved the best fit of the distribution to these data. And when we do that, we will have identified the distribution that is most likely to have generated this sample, or the maximum likelihood estimators of mu and sigma, which describe that distribution. Okay, so that's one way of thinking about maximum likelihood estimation. By the way, I will make pictures of all the pages I create during this lecture, and I will post those to Moodle so that if you want to go back and look at them, you'll be able to do that. So let's think about a second example. Using a discrete distribution, right, as opposed to a continuous distribution. So the distribution, the sampling distribution of X bar that we just looked at is this is a continuous distribution. Values could happen anywhere along this line. With a discrete distribution, there's going to be a limited number of potential values for our variable. And so let's think about this problem. Suppose we have a pool, a large pool, filled with red and yellow balls. Okay, and let P is the fraction of balls that are red. Suppose we draw a random sample from the pool of n balls. And we can say this, let yi equal 1 if a ball is red. So for each time we draw from the pool, we'll keep track. If the ball is red, we give yi a 1 for that trial of the experiment, and we set yi equal to 0 if a ball is yellow. So what we can say is that the probability that yi equals 1, that on any random draw, the probability that a ball will be red is equal to p. P is the fraction of balls that are red. Okay? So we know that, and we want to use our sample to estimate the value of p. Okay, p is a parameter. We've got this pool with thousands of balls in it. We don't really know what the fraction is that is red. We want to take a sample to estimate p. Okay? So, how do we think about this? Suppose our sample has N1, which is equal to the sum as I goes from 1 to N of the yi. So N1 is the number of red balls. And that means that N minus N1 equals the number, so we'll call this the number of red balls and the number of yellow balls. So what we can do then is to say this. We can say the probability of having a sample with N1 red balls and N minus N1 yellow balls is, well, p to the N1 power. What does that mean? So p is the probability that any particular ball will be red. And if we actually observe N1 red balls, then we can take p N1 times, that's the probability of N1 red balls, times 1 minus p to the N minus N1 power. So the probability of red balls times the number of red balls we observe, times probability of a yellow ball times the number of yellow balls we observe, or to the power of the number of yellow balls we observe. Okay, so this thing is essentially it's called a joint probability distribution. Okay, but we're going to think of it a little bit differently, because we're going to our real interest here is in figuring out what the value of p is. And so we're going to write this as follows. A script L, it's kind of an ugly one, we'll give it that little loop there. The likelihood P given N and N1 is P to the N1 power times 1 minus P to the N minus N1 power. So this thing is a joint probability distribution, and this thing is a likelihood function. There's not much difference between the two. It's just a matter of how we write them down. This one is about the probability of what we observe. This one is asking, what's the value of P that maximizes this probability? That's how we're going to use this. Okay, so let me go to the next page. And so let me just write that again. So our likelihood function, which depends on P, is P to the n1 power times 1 minus P to the n minus n1 power. Okay, that's our likelihood function. Now, what we want to do is to find the value of P we want to find the value of P that maximizes the likelihood function. Okay. And when we do that, that value of P that we identify will be our maximum likelihood estimate of P. Okay. So one of the things that we see real quickly when we do this is that it's most often much easier to work with a log likelihood function than it is to work with a likelihood function directly. And so typically what we do is to take the natural log of the likelihood function. And if we do that in this case, we get the following. We get the log of the likelihood. And just taking the log of this expression, we get n1 times the log of P plus n minus n1 times the log of 1 minus P. Okay. So what does this thing look like? Well, I'm not sure exactly, but we're going to have a general idea of the shape of this thing. And so if we draw this, here are values of P, and up here we're measuring the log of likelihood of P. And the likelihood function has some sort of a shape that looks like that. We're assuming that. We'll see if that's true in a minute. And what we want to do is to identify the value of P that is consistent with maximization of the log likelihood function. This will be our maximum likelihood estimate of P, and we're going to call that P tilde to distinguish it from P hat or P bar that we might use for the methods that we've seen previously. Okay, so how do we find the value of P that maximizes this? We differentiate it with respect to P. And so we take the derivative of the log likelihood function with respect to P, and that's going to be n1 over P minus n minus n1 over 1 minus P. Okay. And since we're looking for a maximum, what we're going to do is we're going to set this equal to 0 and solve for P. Okay. So let's see, that means that n1 over P is equal to n minus n1 over 1 minus P. If we cross multiply, we get n1 minus P n1 equals P n minus P n1. Okay. These two items offset each other, and we are left with n1 equal to Pn, or P is equal to n1 over n. What is that? So this thing is our P tilde is our maximum likelihood estimator of P. And what is it? Well, we take the fraction of all balls that are red, and that's P tilde, our maximum likelihood estimator. Well, that's how we would have done this to begin with, right? And what it tells us is that in using the maximum likelihood estimator for a simple problem like this will often lead us to the same place we would have been anyway. But this gives us a way to look at a fairly simple likelihood function and work through this problem of maximizing it. Now, one thing we want to do before we call it a day here is to make sure that our second derivative is negative, so that we can be sure we have a maximum, and that we don't by mistake identify a minimum. And so what we'll do is to take the second derivative. So the second derivative of the log likelihood function, it's kind of messy, is going to be minus n1 over p squared minus n minus n1. Oops, sorry. Tell you what, let's go to a new page and write that so it comes out clearly. So we're taking the second derivative of the likelihood function with respect to p, and that's going to be minus n1 over p squared minus n minus n1 over 1 minus p squared. Okay, n is positive, p squared is positive, so this term is negative since it has a negative in front of it. N minus n1 is positive, 1 minus p is positive. This is all positive. With the negative sign, it becomes negative, and we've just demonstrated that this thing is less than 0. So P tilde is a maximum. It is, in fact, our maximum likelihood estimator of P. So, quick recap. First thing we do is to assume or identify the distribution of interest. In this case, the distribution of P. Second, determine the likelihood of observing the sample we actually do observe. Okay, and we did that by writing down the likelihood function. And then the third, we took that likelihood function and found its maximum. And so the third thing to do is to choose the maximum likelihood estimators, which are the values of the unknown parameters that maximize the value of the likelihood function. Okay, so that's the basic process. And like I said before, I know that the first time you see this, it can seem to be kind of circular, and it's not clear exactly how it works. But through repetition, I think what happens is that you start to see how this thing functions and you can become more comfortable with it. I'm going to stop there, and in the next segment, we will look at how to use maximum likelihood estimation for a linear regression. Okay, and I'll be back in just a moment.